My name is Carlo, I'm CEO of NodeWeaver and the original architect of the platform. And I will present a brief overview of the one of the way that we use to control a NanoCloud, which is through the web browser. But actually, this is just a thin layer on the core engine, which is API-based. So everything that you see here can also be done through our APIs, command line tools, or external services like Ansible, Terraform, Salt, or Puppet. The key idea behind NodeWeaver is that it should behave exactly like a public cloud. So it should be a transparent service and should hide the hardware properties of what it's run on, because in this way, we are able to provide an easier manageability, especially when you have thousands of locations with different hardware devices. The system basically is based on a set of small binary objects called probes that constantly check on every physical node. The behavior of the system as a whole, they provide you indication about how it's working, if anything is not right, and it gives you a sort of a synthetic probability if a failure is going to happen and in what time. The key idea is starting from the bottom, we see the view of the hosts, which are different. One is basically a smaller one, one is a bigger one. And for each of the system, we can get a lot of information about this. Whether it does have a IPMI, what kind of sensor does it have, what kind of capabilities that the CPU have, the speed, the individual disk properties. It's something like 300 different probes that are used to get information about everything and collect this into a global view of what this node is doing. The important thing is that the administrator has nothing to do to let's say, change the properties of it. Everything is done by the system. You can only disable it if you want to put it offline. Or if you want to reserve resources like CPU or memory, you can do that. But basically, that's the only thing that you can do. And the same applies to the distributed file system, which is based on the idea that everything that is written or read here is divided into small data blocks called chunks. Chunks are then replicated across all the storage devices, which can be anything. You can have one node with 2 rotational units and an SSD. You can have another node with, I don't know, NVMEs only. The system will decide where to place this to provide the maximum throughput and the lowest latency. And it does things like identifying whether a system allows for compression, whether, for example, a device is starting to fail or is still becoming to slow down, and it does have a full CRC traceability. So we're able to identify whether something is corrupted, and we're able to repair it in real time. And from this layer, we build the virtual capabilities, like virtual networks. Each node has its own virtual switch. They're all interconnected. We can create any number of virtual network, which can be plain or VLANs or VXLAN, and assign to this IP addresses or pure MAC addresses if you want to bring something that comes from a physical world. We have a security layer that is built directly in the hypervisor that allows for packet filtering. We do have quality of service, so we can limit traffic. We can provide reservations, so you can make sure that one workload will have a higher priority compared to others. The same applies to storage, where we can create virtual images, and we combine this into what we call templates. Templates are basically a sort of a blueprint that we use to create resources. Blueprints can have a fixed amount, for example, of CPU or memory, or can support hot resize if needed. We can attach any number of virtual disks, any number of virtual networks. We can specify things like what kind of firmware you want to use, what kind of emulation we want to use, including Hyper-V emulation, if you're bringing workloads back from Windows or from Azure, we support a very important capability, which is called the context. When we deploy one of these templates, we are able to modify everything. We can inject variables, we can inject scripts. So, for example, if you have a Windows VM, we can have this automatically join Active Directory, or if you have a Linux machine, we can specify new packages to be installed. We can even take advantage of variables. For example, we can take variables like the geographic position of the cluster to say this cluster is in Europe, so deploy this VM so this GDPR compliant, or this cluster in Japan, so adapt it to the local legislation. And we can do things like specify scheduling. We can have auto scaling, we can have affinity and anti-affinity, and so on. And of course, instances can be, let's say, modified. You can expand them. You can connect to the local console. You can live migrate it. You can shut down. You can take a live snapshot. Because one of the nice things of having a transactional data store behind is that in any moment we can take a snapshot that is live, that is consistent, and that can be immediately used to create another VM, or it can be exported and used as a disaster recovery site. And all of this starts and ends with the idea that everything that regards the hardware is managed by the platform, no matter what happens. Everything that regards the virtual resources is left to the user, and we support as many different interfaces and API as possible to be able to fit into whatever mechanism that the end user, the end customer wants to use.
Okay, let's back up to the storage, because that was like the first thing you showed. Do you have to use the DFS, or can you kind of develop your own storage underneath?
Right now, you have to use the DFS for starting the native workloads, but you can use the VMs to create an additional storage layer. So if you want to use Rook to install Ceph, for example, you absolutely can do it. We have customers that use MinIO to provide S3 services, and they basically simply say, I don't want replication. I will handle it on my own. And you're absolutely free to do it. And you can even change in real time. So you can have what we call Gold 1, which means I don't need replication. I will handle storage myself. Mm-hmm. And if you find out that you need something different, you can switch in Gold 2 or Gold 3 or any other goal live while the VM is running. And the system will start to replicate it in real time.
Okay. Okay. And this, the DFS that you developed for this, is this based off of an existing open source project?
It's based on a host of different open source projects. This actually comes from a bunch of European projects that were designed to create a distributed file system for high performance computing. So it's based on a hybrid between two projects called MouseFS and LizardFS. And basically, we created our own version of it. And we support it, and we even created the layer to export this to other systems like Fuse or NFS and so on.
Okay. And it supports different levels of like replication and redundancy depending on your needs?
Exactly. There is an attribute which is called the goal. Goal is a metadata that is part of the virtual images. And the goal basically tells the system what kind of strategy should I use to place these blocks on whatever storage is available. So we see here that we do have basically two hosts, and each host has multiple disks. In this case, basically the system will take advantage of the fact that we are able to read in real time the information about things like bandwidth, latency, the IO queue, outstanding requests.
Well, I'll just mention real quickly that the goal level is, by the way, not platform wide. It's individually selectable at the virtual
Image.
disk image level. So if you want one virtual disk image to run really fast and you want 2 copies and lock it into solid state disk, you can tell it, I just want to lock that in. Or if you want something that's maybe like video surveillance data and you want it on cheaper rotational media, you can say for this data, for this virtual hard drive, I want 3 copies and I want to lock that into rotational media. But it's on an individual virtual hard drive or virtual disk image by disk image basis.
We talked about you being bare metal directly on the hardware, and then you talk about creating VMs and containers and stuff. Like, how does the hypervisor then layer into this? How does that operating system we use for container deployments layer into this?
Yeah, the key idea is that we take full control of the hardware. And on top of this set of software modules for the distributed file system and the virtual switch, we have this multiple choice of different hypervisors, which are selected by the system. So everything that runs in NodeWeaver, actually, every workload that runs in NodeWeaver runs in an hypervisor. However, there are hypervisors that are, let's say, fully fledged with all the emulation that you want, all the drivers that you want, including we have an hypervisor for running VMware workloads. But if we recognize that we are running something that can support the para-virtualized drivers, we do so. So basically, it becomes a full pass-through. So we always run an hypervisor, but it's as thin as possible, considering what kind of workload you want to run.
So it's your own hypervisor, like a modified KVM or something like that.
Yes. We have the legacy hypervisor is a modified KVM with a significant number of added drivers, especially for emulation from other vendors. And we have the thin VM one, which is similar in design to Kata containers. It's not based on Kata containers, but it's quite similar. And basically, it was developed in parallel with them.
Okay, so if I wanted to use VMware, we'd layer NodeWeaver on there and then create, I'm assuming there's this defined process to say we want to load VMware on here, and it would load that up, and I'm assuming that would be a direct pass-through so that it can access the hardware directly and run those virtual machines, and you just kind of sit there sort of to the side, letting it do its thing.
Yeah, we still use, let's say, the KVM layer is still used for CPU partitioning. But the actual, let's say, loss, performance loss due to this kind of pass-through layer is very limited. It's less than 3-4% at maximum. So we do have customers that run VMware on top of NodeWeaver. NodeWeaver runs in NodeWeaver. That's actually how we develop it. Being able to do pass-through, it's administrator controlled. So the admin decides what devices we want to pass through, because some pass-through may be dangerous.
Yeah.
For example, it's normally used for pass-through GPUs, so that you can do deep learning or whatever kind of desktop you want to. We do have a pass-through for FPGAs and so on, and it can also be used for the disks and for the network. This screen that you see here is actually coming from one of our customers, which is a very big car parts manufacturer. And they use NodeWeaver to run a proof of concept for having a device inside of self-running of self-driving cars in Detroit, I think. They had a box that had to collect information at 40 gigabits per second, because it's the rate at which the sensor generates. And that is the actual performance that was measured by them. Basically, in bare metal, they had CentOS 7 and Ubuntu 20.04 running on the bare metal, which was a Supermicro box. And the same with Ubuntu running within a NodeWeaver thin VM.